Okay guys, in this video lesson we're going to start taking this idea of momentum and start looking at it through the lens of conserving. Okay. Now, when we have a scenario where two objects are colliding with each other. Okay, so right now we have our Newton's cradle object kind of going back and forth, back and forth. Same idea of these pictures here. When we have those scenarios where there's a collision or there's an interaction between two things, we've found out previously that the energy in those collisions may not be conserved. For momentum, that's not true, okay? That's what makes momentum very useful for us, is because for momentum, when we have a collision, momentum is conserved between objects, which means if I know the momentum of this sphere as it hits here, I can determine the momentum of that sphere when it leaves. And if I know its velocity, I can find out that one's velocity also, or its mass here to mass over there, all right? Now, things that we need to consider as we go through this idea of conserving momentum in collisions. First of all, total momentum of the system does not change, all right? Which means if you started with 675 kilojoule or kilograms meters per second of momentum, you end with 675 kilogram meters per second of momentum, all right? If you start with zero momentum, you end with zero momentum. That one seems kind of weird, but in reality, that actually is very useful for us as we do look at some of our practice problems, okay? We want to always compare momentum before versus after and realize that we can transfer momentum between one object to the other. Keep in mind also that direction here really matters, all right? As two objects are hitting each other and bouncing off, going left and right, up and down, those kind of things, we need to be able to track the direction because a velocity to the left will be opposite or a different sign than a velocity to the right as we do these math, okay? So let's do the actual equation for this. Now, in a collision of two objects, momentum before the collision has to equal momentum after the collision, which means the momentum, remember P is momentum of our first object initially plus the momentum of our second object initially will equal their momentums afterwards, all right? Now, the changes don't have to be the same, but these two added together have to equal these two added together at the end, okay? Also, watch out for zeros here. So it's very possible that some of these objects will not be moving either at the start of a scenario or at the end of a scenario. So if something's not moving, it has no momentum, okay? Take this equation and break it down into something a little bit more useful for us. We now have our masses and our velocities separated out, okay? For example, if object 1 is moving at 10 meters per second and object 2 is stationary at the beginning of a problem, well, that means this would be a 0 for us. If at the end of the collision, object 1 is no longer moving, but now object 2 is moving at 5 meters per second, that tells us something about the mass differences between object 1 and object 2, okay? And we can mathematically work these things out. But it is important to note that sometimes we have things standing still, which is helpful in our math, all right? Now, the beauty of having this work the way it is we can use this equation to find masses and velocities. With energy, we can't, because whenever you have a collision with energy, you have a loss of energy to either thermal, deformation, sound, or other sources, which means you can't solve for masses and velocities before and after a collision using energy. But for momentum, we can. So that's where this equation becomes very useful for us, is we now can actually solve for masses and velocities through a collision. All right, so here we go. First of all, let's do a concept check, okay? A Honda Civic has a much smaller mass than a Chevy Suburban, okay? So Civic is low mass, Suburban high mass. Moving at 50 miles per hour to the east, all right? Collides with Suburban moving 50 miles per hour to the west. Okay? That's good to know because this would make, if we make this a positive 50 miles per hour, this would be a negative 50 miles per hour because they're doing opposite direction. What direction is the Suburban moving after the collision? Is it moving faster or slower than before? Okay. Take a minute, think it through, and then I'll give you the answer in a second. All right, so let's go to the answer. Well, the Honda has a smaller mass than the Chevy, right? Which means when they collide, it has less momentum than the Chevy does. Not just because it's smaller, but because it's also moving at the same speed. So because velocities are the same, it's going to have less momentum with it. Now, As a result of that, when they collide, the Chevy Suburban has more momentum. The Honda has less momentum, which means, in terms of what's going to happen after that collision, there's going to be extra momentum moving to the west than there was to the east, okay? Which means at the end of it, the total momentum has to be still moving towards the west. So the Suburban is still going to be moving west, okay? Now, what happens to that Honda Civic? I don't know. Does it get crumpled up and thrown into the ditch? Does it hook onto the Suburban? They both slide to the west. Does the Suburban, is it all like jacked up with big tires and drives over top of it? I don't know. But we do know that in a pure physics sense, after this collision is over, the Suburban will essentially win this battle, and it will kind of keep moving to the west. Now, keep in mind, this is not a good scenario for either person, but in terms of the collision, the Suburban is going to slow down and keep moving in the same direction. The Civic is essentially going to probably stop and possibly even be forced backwards in this scenario, which would not be good. And we'll talk about that more in our later on video lessons on this. All right, we'll be moving faster, slower. It'll be moving slower. Okay. Now let's do a math check. We have a 5 kilogram ball, and we're going to move it into an 8 kilogram ball. Initially, the 5 kilogram ball is moving at 10 meters per second. It's going to hit a stationary, which is useful for us, 8 kilogram ball. After they collide, 5 kilogram ball will move backwards. Okay. So if we're going to show from left to right across the screen, this is our forward direction. Afterwards, it's going to bounce off and go backwards at 2 meters per second. Make sure when you do your math, this is moving forward at 10 meters per second. This is backwards at 2. So one of these two velocities, you have to tag with a negative sign. It really doesn't matter which one you do, but they both cannot have the same sign to them because they're opposite direction. We're going to solve for what's the velocity of the 8 kilogram ball. Okay, so organize your equation, set up all of your variables, and then solve for the velocity of the 8 kilogram ball afterwards. But before we do that, let's see it happen. So this thing moves in, collides. After the collision, this will move away, and this one moves back. Okay. The ending velocity is negative 2 meters per second. We want to know what's that ending velocity of that 8 kilogram ball. Okay. Pause the video, try to work it out, and I'll give you the answer in a second. All right, so let's take a look at our answer here. We have our basic equation. Initially, the 5 kilogram ball is moving at 10 meters per second. The 8 kilogram ball is not moving at all, so that's a 0 for us. After the collision, that 5 kilogram ball was moving in the opposite direction at 2 meters per second. And the 8 kilogram ball, we had no idea what its velocity was. So we're going to solve for this V2F here. Rearranging the equation, we can then bring this over here. 50 will then equal a negative 10 plus 8v of the velocity. Solving for this, do a little bit of algebra, and we end up getting 60, okay, because it's 50, which would be minus a negative 10, right? So 50 minus a negative 10 is actually 50 plus 10. That's why that negative sign is important to us. So we end up getting 60 here divided by 8 is 7.5 meters per second, okay? If you got a value of 40 here, you probably didn't track this negative sign properly either from the beginning or through your algebra as you did this here. All right, so we end up going at 7.5 meters per second, and notice how this is positive because this ball was moving to the right or in the positive direction at the end of this. Okay, that's our math check. Here's an additional practice problem that you can also do. This one has a little bit different scenario to it. We have a 35 kilogram kid running and jumping on the back of a stationary toboggan with his friend on it. The toboggan moves at 2.5 meters per second. If the friends at toboggan have a combined mass of 90 kilograms, how fast was the kid initially running? A little bit different twist to this one, so let's take a look at what's kind of going on. First of all, here's our basic equation. But in this scenario, we have one kid sitting still, we have another kid running and diving basically on top of him. Now, if anybody has ever gone sledding in Minnesota for more than 2 to 3 minutes, this happens all the time, right? One kid jumps, dives on top of the other one, they go down the hill together, or they do it on purpose to do something. I see it all the time with my little kids. Now, take a look at the change here though, okay? Because the two objects, after they collide, or after he jumps on top of the toboggan, they stick together, okay? It's kind of like that perfectly inelastic collision we talked about before. So they each had their individual masses and velocities before, but at the end, when they're on the toboggan together, their masses combined have one final velocity. So we can take this equation and we can simplify it or rearrange it essentially because the velocity of object 1 and object 2 are the same. We can create this, okay? Now it's much easier to solve for that final velocity because it sits right here. Oh wait, we know the final velocity. I apologize. We know the final velocity is 2.5. We don't know the initial velocity of one of our kids here. Okay? From here, go ahead and try to solve it, and then we'll give you the solution. All right, here we go. If we take our numbers, oops, I went one too many. Take a look. We have our original kid running. We don't know that person's velocity. The other kid in the toboggan were sitting still. That was the other 55 kilograms of that mass. At the end, their combined mass, we're moving at this speed. So we're solving for VI. Rearrange this, and we get 6.4 meters per second. Okay? All right, guys, we're going to end the video lesson there. In our next segment, we're going to talk about what happens when we change momentum through the collision itself. Thank you.